The universe hides phenomena so astonishing they rewrite physics, and you've never seen them explained like this. Stay tuned, because number 1 is a revelation almost nobody predicts. Imagine a faint glow left over from the birth of everything, stretching across the sky like an ancient whisper. Discovered in 1965, the cosmic microwave background is a uniform radiation field at just 2.7 Kelvin, providing the strongest evidence for the Big Bang theory. Tiny temperature fluctuations in this afterglow map the seeds of galaxies, allowing scientists to calculate the universe's age and composition. Researchers continue to refine measurements to test inflation models and dark matter theories. Up next, we'll explore bursts of mysterious radio signals that flash across the cosmos in milliseconds.
Witness the sudden, millisecond-long flashes known as fast radio bursts, puzzling astronomers since their first detection in 2007. These powerful pulses originate billions of light-years away, releasing as much energy in a heartbeat as the sun does in days. While the exact sources remain debated, theories range from magnet Rs to exotic astrophysical phenomena. Recent observations of repeating bursts have allowed precise localization to distant dwarf galaxies, narrowing the mystery. Scientists are now using global networks to triangulate these signals in real time, hoping to turn FRBs into cosmic probes of intergalactic matter. Next, we turn to a force that silently pushes the universe apart.
Did you know that an invisible pressure called dark energy is accelerating the expansion of space itself? Accounting for roughly 68% of the universe's total energy density, dark energy was inferred from observations of distant supernovae in the late 1990s. Its repulsive effect counteracts gravity on the largest scales, causing galaxies to drift farther apart faster over time. Although its nature remains one of the biggest puzzles in physics, models such as the cosmological constant and quintessence attempt to describe it. Upcoming missions like the Euclid telescope aim to map its influence more precisely. Soon we'll hear about ripples in spacetime that were finally felt on Earth.
Hidden within the fabric of spacetime are gravitational waves, tiny distortions that travel at light speed. Predicted by Einstein a century ago, they were first directly detected in 2015 by LIGO when two black holes merged 1.3 billion light-years away. Since then, dozens of events, including neutron star collisions, have been recorded, opening a new era of astronomy where we listen to the universe. These waves carry information about mass, spin, and even the equation of state of ultradense matter, unreachable by traditional telescopes. Now let's dive into the cataclysmic collisions of the densest stars.
Surprisingly, when two neutron stars spiral together, they unleash fireworks of heavy elements and a burst of gamma rays. The 2017 event, observed across the electromagnetic spectrum, confirmed that such mergers forge gold, platinum, and other rare metals, dispersing them into interstellar space. The resulting kilonova glowed brightly for days, providing the first direct link between neutron star collisions and the origin of heavy elements. Gravitational wave detectors captured the inspiral, while telescopes recorded the afterglow, demonstrating the power of multi-messenger astronomy. Our next stop is the giant lurking at the heart of our own galaxy.
Astronomers have mapped a supermassive black hole, Sagittarius A*, whose mass is 4 million times that of the Sun and sits at the Milky Way's core. In 2022, the Event Horizon Telescope captured its shadow against surrounding hot gas, offering the most detailed view of a black hole to date. This behemoth governs the orbits of nearby stars, and occasional flares reveal how matter spirals inward before disappearing beyond the event horizon. Understanding such objects helps scientists test general relativity under extreme conditions. From there we venture to worlds beyond our solar system, where we can actually sniff alien skies.
Scientists now analyze the thin layers of light filtering through exoplanet atmospheres, revealing water vapor, sodium, and even possible signs of life. By measuring the spectrum during a planet's transit, they identify chemical fingerprints that indicate temperature, cloud composition, and potential biosignatures. The James Webb Space Telescope has recently detected carbon dioxide and possible phosphine on distant worlds, sparking intense debate. These techniques transform distant points of light into detailed planetary laboratories, expanding the search for habitable environments. Beyond individual planets, some regions of space are almost completely empty.
Rarely do we find cosmic voids so vast that they contain hardly any galaxies, stretching hundreds of millions of light-years across. The Boötes void, for instance, spans about 330 million light-years yet hosts only a handful of faint galaxies. These empty bubbles challenge models of large-scale structure formation, suggesting that dark energy and dark matter interactions shape the cosmic web's filamentary pattern. Studying voids also offers a pristine laboratory for testing theories of gravity, as fewer massive objects mean fewer gravitational disturbances. But the most energetic explosions in the universe await.
Incredible gamma-ray bursts can outshine entire galaxies for a few seconds, releasing more energy than the Sun will emit in its whole lifetime. They fall into two categories: long bursts linked to massive star collapses, and short bursts associated with neutron star mergers. Detected by satellites such as SWIFT and Fermi, these flashes illuminate the early universe, allowing astronomers to probe star formation just a few 100 million years after the Big Bang. Their afterglows, observed across the spectrum, provide clues about the surrounding interstellar medium and the mechanisms driving the jets. Finally, we confront the ultimate perspective, the sheer size of everything we can see.
Finally, the observable universe spans roughly 93 billion light-years in diameter, a sphere of light that defines the limits of what we can ever detect. This boundary, set by the age of the cosmos and the speed of light, encloses billions of galaxies, each containing billions of stars. Its sheer scale forces us to confront how much of reality lies forever beyond our reach, while also highlighting the extraordinary reach of modern telescopes and surveys. Understanding this horizon informs cosmology, dark energy research, and the quest to map the ultimate shape of space-time. The enormity of this vista underscores why each of the phenomena we explored matters. Each is a window into a universe far larger than imagination.
We've traveled from the faint afterglow of the Big Bang to the staggering scale of the observable universe, witnessing how each discovery reshapes our cosmic story. These 10 phenomena show that the universe is far stranger and more beautiful than we ever imagined. If you enjoyed this journey, subscribe so you don't miss the next mind-blowing list we release every week. Which of these cosmic wonders left you the biggest impression? Let me know in the comments, and if you liked the video, give it a thumbs up. Thanks for watching.